Hey everyone, good morning, good evening, good afternoon, whatever it is for you. I hope you're doing well. This lesson I'm going to go over statistical significance, and it's kind of similar to what we went over in the previous lesson about how we want to prove something is statistically significant when we do a study, and something that is statistically significant is something that is so rare to happen that we kind of analyze it and we see that this is usually used in experiments. So we see that our treatment mostly is working when we prove statistical significance, and that's a good thing. So there's a bunch of vocabulary here, and I'm going to try to paraphrase it to the best of my ability. There's something new here. It's called the Null Hypothesis. The null is, sometimes you'll see this is this symbol H naught. It's the assumption that there is no effect of the experiment's treatment. You always assume the null is true until you have evidence against the null. The null for our cases is going to be that there is no difference. So if you remember in the last lesson we went over diff, which is the difference between the means of two groups. So I kind of think of it as like innocent until proven guilty. So what I mean is that we always assume that our null is innocent, meaning that we always assume that our null is zero until we prove that there is some statistical significance to say that our study is statistically significant. I hope that makes sense. So then it says, when working with the null, with the differences of means, the hypothesis is always that there is no difference in the means. Like I said, this is the assumption that our subtraction would make us have a difference of zero, or the fact that mean A would equal mean B, which means that, there's no difference. So essentially the two groups being studied have the same mean or very similar mean. That's our assumption originally. And when they're very different, then we have something called statistical significance. What is statistical significance? It's the likelihood that the result of a relationship is caused by something other than mere random chance, which means that in an experiment, it would be the treatment, and that's what we're looking for. Something that is statistically significant if it was unlikely to happen if the null were true. So that means that if it was true that there was no difference in the means, and we saw something that was statistically significant and it was unlikely to happen, then the null would be false and we would reject it. And we usually use this rule of thumb: anything outside of 2 standard deviations is considered unlikely. What this means is, if you look over here, is we know that the bell curve looks like this. 2 standard deviations would be approximately here, like this is -2 and this is +2. Within this is 95% of the data, which means that there'd be 5% left over, which would leave 2.5% here and 2.5% here. Something is statistically significant when it lies within these tails of the bell curve. Something that is so rare to happen, it is not within the bulk 95% of the data. So when we say that we use a p-value from the previous lesson of 2.5%, we reject the null. And that's because it is less than the area in which it would be considered rare to happen. So we don't want to be here because this is the normal. This is the mere random chance area because this is what would normally happen. Here and here, depending on what you're analyzing, would be considered the statistically significant regions. Now there's also a 90% level, and it's very similar. It means that 90% of the data would be here. What's left over? 10%. So that means that 5% is left here and 5% is left here. So this is another p-value you can use. So there's a p-value of less than 2.5% we can use as a rule of thumb to state something is statistically significant. Or some people use a p-value of less than 5%. It really depends. Some people like to use the 90% because they might not get the p-value that they desire. And I'll say what I mean when we do an example. But the better one is this 95%, because if you're 2.5% or lower, that's really, really small and has a rare chance of happening. So that's more statistically significant. Okay, so what's the goal? Oh, I'm sorry, let's go back. It says resampling. So you're going to see a bunch of bar graphs and dot plots in this lesson. That's created usually by a computer generator, which is just resampling the data that you already have. It's a quick and easy way for statisticians to see their data in another light. You could also always go out and take more samples, which is the better way. But when you don't have that chance to do, so basically it takes money to do studies. So if you don't have the money to do a study, you use the computer to resample for you. If you did have the money, then you can go do more samples and get a better view of data. But majority of the time, they do use computer simulation. The goal of statistical significance, we want to see if the value you're testing is unlikely if the null were true. That occurred if such a value did not happen due to pure chance. So that's again what I was talking about with the low p-values. So we will reject the null, and again the null means no difference. So remember, our null is that we're assuming that there's no difference in the means. So we always assume that 0 is the difference. You're going to reject the null when you obtain a very small p-value. If there's a small p-value, small probability of obtaining the difference of extreme more than 0, the difference from the experiment is unusual and not typical of chance behavior. Not typical. And that's when we say something is statistically significant. When something is not typical of chance behavior, we say it is statistically significant. If there's not a small probability, then your difference value from the experiment is not considered unusual and typical of chance behavior. The result is not statistically significant, and we fail to reject the null. So this is a kind of a phrase we're going to use. So either you're going to reject the null, or you're going to say we fail to reject the null. To reject the null, like I just said before, use confidence levels. And that's what I was doing with the bell graph. 95%, you're looking for a level of 2.5%. And I really should have written in here, I had to make an edit for next year, this is a 90% confidence level. Okay, so if you look here, all the way over here, this is what we're talking about. Okay, so this is your 95% confidence level. This is your 90% confidence level. So let's apply this to an example. So Carlos is doing an experiment on monarch butterflies. The new monarch butterflies have different coloring patterns, and they appear to be larger than the traditional monarch butterflies. Oops, okay. He collects 4 of his new butterflies and 4 traditional butterflies and measures their wingspan. So what's the experiment analyzing? The response variable is the wingspan, okay? And releases the butterflies. Of the 8 butterflies he collected, he observed the difference in means. This is an observational study, actually. It's not an experiment because we're observing, but we are measuring something. So I'll take back my comment of a response, but it's a measurement of wingspans. Okay. He finds out that the difference of the means of his 4 butterflies and the mean difference of his other butterflies is 0.5. And we can see that's over here on the dot plot. The dot plot below shows a randomization of 70 resamples. That means that there were 70 dots, 70 resamples, either done by a computer or Carlos did 70 resamples of measuring butterflies and then subtracting their difference in means. So if you remember back to the tomatoes from the previous lesson, what is happening is he has a group, let's go over here. He has a group of 4 butterflies. Let me see if I can write here. Okay. Oh, that is a terrible butterfly. 1, 2, oh God, this is bad. Okay. 4. That's group A. Kind of like the tomatoes. Group B. I am not an artist. That is okay. This is group B. So whatever their numbers are, he's adding them all up. And let me just move. He's adding them up, dividing them by 4, and getting a mean. Mean A, mean B. And then he subtracts those means. And he got in the first sample 0.5 centimeters as difference. He's doing that 70 more times. I hope that makes sense. That's what's happening here, just like the tomatoes from the previous lesson. So Carlos is hoping that he has made significance in his discovery. Use the given information in the randomization test of 95% level. Now this is awesome because they're telling you what p-value they want you to use. this is telling me that I'm going to use a 2.5% rejection region, which means that if it's less than 2.5%, I will reject the null, and that his difference is not due to random chance, and it is statistically significant. If my p-value is above 2.5%, I'm going to fail to reject the null because it is not below this level of significance. So let's see what we got here. Whenever we're going to analyze his difference of 0.5 centimeters. So that means, since it's on the left side of our bell, if you guys can see your bell curve, this is approximately symmetric. Whenever you're on the left side, you are going to go a p-value. Your p-value is always going to be a diff greater than that value, so greater than 0.5 centimeters or equal to, okay? So how many are there? 1, 2, 3, 4, 5, 6, 7. 7 out of 70. Okie dokie. So we have 7 out of 70, which will give us a value, if you guys divide in your calculator, of 0.10, which tells me 10%. So 10% is here. That is 10% right there. Is that statistically significant? No. It is not less than this 2.5% level. It's not even less than the 5% level for the 90% level of confidence. So he did not see something statistically significant. He saw something due to mere random chance. So we're going to write a conclusion here, and you always have to make sure your conclusion is in context. So we're going to say, and forgive me for my handwriting, Carlos's difference is not statistically significant, stat sig, because his p-value for 0.5 centimeters or larger is, let me just move this so I have more space to write, is 10%, which is not less than 2.5% for a 95% confidence level. To get full credit, you have to write all of this. It's not hard. It's going to be pretty much the same. And we have one more thing we want to state. We're going to say, we will say that since we did not see something was statistically significant, we will fail to reject the null hypothesis, and Carlos's observed difference was most likely due to chance behavior. Meaning that the butterflies probably always will have that wingspan. This is a very similar example. The only thing different here is we have a bar graph, if you guys can notice. And also in this example, they don't tell you the difference. You have to calculate the difference, but we can handle that. We know how to subtract, so we're going to be just fine. So in this example, we're analyzing bamboo. Bamboo had become an increasingly popular home construction product due to the fast-growing nature of the bamboo plant. The yearly growth of 1-year-old bamboo plants was studied under two conditions: the mean heights of 100 plants grown in an indoor field and 100 plants grown in an indoor facility over 1 year shown below. So we have a mean for outdoor, we have a mean for indoor. These are the two means we're going to analyze. A randomization test is undertaken. Due to the large sample size, a computer, so like I said before, sometimes they use a computer to make their lives easier, is used to simulate a distribution of the differences. This is a simulation. In the mean heights, there are 2,930 simulations. So that means like on the dot plot, there were 2,930. And that's what we're going to divide when we find our p-value. We're going to use that as our divisor. Okay. And they resampled or reported in histogram shown below. Okay, so we got a histogram. Great. And we also want to make sure we are reading and seeing that this is in hundreds, which would be a problem if you don't do that, because this is 100, 200, 300, 400, 500, 600, which means that this is 0.5, which would be 50, and over here would be 0.25, which obviously is 25, and so on and so forth. Okie dokie. So to determine if the mean and the growth heights, A, Determine the mean difference in the growth heights of outdoor minus indoor. All you got to do is take the numbers up there and subtract it for them. 86.9 minus 97.2 inches. We'll get a difference of negative 10 point, I think it's 3. Yep, negative 10.3 inches. So they say explain the meeting in the context. I'm going to move it over here. Sorry, I can't fit there. So we're going to state that the indoor group has a greater mean by 10.3 inches. That's it. Okay. Now we're going to see if the observed difference is statistically significant. Now notice here they do not give you a level of confidence. So it's really up to you. You can use the 95% level. And remember, if you use 95% level, 95% has to be less than 2.5%. And if you use a 90% level, what I mean by it, the p-value. The p-value for 90% would have to be less than 5%. Okay, so really up to us or you, what you would like to choose. I always try my best to choose the 95% level because the p-value is very small. It's 2.5% or less, so that's like even better to prove statistical significance. So we want negative 10.3. That's what we're going to analyze. When it's negative, you're going to go to the left. You want to analyze the left side of the bell curve. So negative 10.3, I'm going to look at the bar from here and on. This is a bar, and actually I just realized that this is a bar, so we're going to have a different p-value than I had before. Okay. This value is about 25 right there, and this value is about 5, because that's 12.5 right there. So if I add these together, I get a value of 30. To find my p-value, I would get 30 over 2,930, because that's how many dots, or in this case bars, we have. Not bars, the value, the amount of dots inside of the bars, would get me a value of 0.0102, which gets me 1.02%. Now, they don't tell you what type of level they want you to use, so I always try to use 95%, which means that I want my p-value to be less than 2.5, which is true here. So, since my p-value for the difference, I want my context here, of outdoor minus indoor is 1.02%, which is less than 2.5% for a 95% confidence level. My observed difference is stat sig, and we will reject the null. The observed difference is not due to chance. So I hope this helped, and have a great day.